Hello everybody, we've got some factoring to do here. I've got several examples listed here, so if you see something you prefer, just skip to it. But we're going to start out and do these in order. Number one, this is trinomial, and what you should look for when you're doing these trinomials is before you attempt the binomial approach, which was illustrated earlier, look for a GCF before you start anything. In fact, in any factoring problem, always look for a GCF first. It could save you a lot of time and also make the difference between getting the right answer or the wrong answer. A complete factorization or an incomplete factorization. So that's what I do on this first one, and I noticed that there is a 5 that's a GCF, so I would immediately pull that out, put it in front. I get this expression. So that would be my first step. Okay. Second step, I notice that this thing might be factorable further, so I try it. And I don't have a lot of choices. Remember, I need two numbers whose product is positive 5 but add up to negative 6. After a little bit of thought, I come up with minus 5 and minus 1. Okay? Notice that they do add up to negative 6, and the product is positive 5. So that one is good. Okay, let's try the next one here. Now this is a different type of problem. We haven't seen this before. This is a special type. It's a binomial, but it happens to be the difference of two perfect squares. In fact, each of these examples here in problem 2, if you'll notice, the two terms are perfect squares. 4 is a perfect square, and so is x squared. 25 is a perfect square. 9 is a perfect square. Y squared is a perfect square. 36x squared is a perfect square. And 1 is a perfect square. And they all have minuses. Now, if this is the case, then we can factor these just by taking that square root of the 25 and the square root of this and putting them together, like so. So one of them will be a 2 minus, the other one a plus, but the numbers are the same. The 2x and the 5, they come from the square roots of 25 and 4x squared. This next one is 9 minus y squared, so identify the squares here. It looks like we have 3 squared and y squared, so this answer would be 3 minus y and 3 plus y. This next one, again, we notice we have the perfect square, so the square root of the 36 would be a 6, but I need the x to go with it. So 6x and 6x. And then the 1 is a 1, so square root of 1 is 1. So 1 plus, 1 minus. And those would be my answers for those. Now, sometimes you get something that doesn't quite look like a perfect square, like the difference of two squares. Like this one here. 10 is not a perfect square, neither is 490. But we notice that using the first approach, like in number 1, we see a GCF in here that we could pull out. So if I do that first, pull that 10 out, I get this, which then coincidentally leaves me with the difference of two squares. So I can continue like so. And I now have these complete because I know I can't factor these any further. These are first degree, no GCFs within each of these factors, so it's all done. The next one looks a little strange because it's got an x to the 4th here, and it's also got a 3, so it almost doesn't look like we have perfect squares at all, but let's work on that 3 first. It is a GCF. So we get this. Then we look at this and notice, well, this could be considered a perfect square also. In other words, x squared minus a 4. So 4 is the square root of 16, and x squared is the square root of x to the 4th. And then x squared plus a 4. Okay, now we haven't seen this before, and it looks like we have another difference of squares in here. This is the sum of squares, which, by the way, cannot be factored over the real numbers. Okay, sum of squares. Don't try to factor it over the real numbers. If it's in this form, can't do it. So we take this one more step. Make this x plus 2 and x minus 2. And leave this other one here, the x squared plus 4, because you're done with that. It's prime. As far as we're concerned, it's prime. So this is my final answer now, completely factored. This first was a partial factoring. The second expression was another partial factoring, incomplete. The third is complete factorization. And that's what we strive for in all these problems, complete factorizations. Okay, now, these next three are special cases of what are called difference and sum of cubes. Notice that 27 is a perfect cube. And the first thing to do is identify the perfect cube. In this form, we're not going to go into its derivation, but you'll see that x minus 3 will be our first factor, and then we'll have an x squared and a 3 squared out here. So in that sense, it kind of looks like the binomial, the difference of squares that we did here. This will be a plus, kind of, but we've got these extra powers in here. Also, we're going to end up with an extra term inside here. It'll be plus, it's the opposite of the first sign here, so it'll be plus, and then it'll be the product of the x and the 3. So it'll be a 3x. Now I probably wouldn't leave this as a 3 squared. I just wanted to show you where our final answer comes from. The final answer looks like this. I would just make that change like so. And as long as this is a second degree here, then you can be pretty sure this won't be further factorable. As long as you've got a GCF pulled out right away, you shouldn't have any other questions about this trinomial. It should be factored in that form. Okay, the next one, identify this 8 we see is actually a 2 to the 3rd, isn't it? So the second problem, we'd have an x. This time, since it's a plus, we go with a plus 2. And then we put in the rest. We'd have an x squared, and we'd have a plus 4, because that's 2 squared. In the middle now, instead of being a minus the way it was over, plus the way it was over here, which is the opposite of the first, it would actually be the minus 2 times the x, so a 2x. That would fill in that. That's complete now. Okay, the next one poses a little bit of an issue because 2 is not a perfect cube, neither is 54. However, as a preliminary step, you could factor that 2. I don't know if you were on the lookout for that. Get this, and now it just happens to be a perfect cube, 27. If it weren't, then we would be finished here. If this were like a 25, for instance, we would be finished. If this would have been 2x to the 3rd plus 50, we would have been done after this GCF was pulled out. But here we have to look out for this. This can be factored a little bit further. So we'll do it. We have a 2. We notice it's the cubes again. This time sum of cubes. We'll have an x. And you'll have a plus 3. This 3 cubed is 27. Oops. It's a cube there. 3 cubed 27, and then over here we'll have an x squared, and we'll have a 9 over here because 3 squared is 9. Okay, and then here we're going to have a minus. Okay, Okay, it is going to be the opposite of that first term, and it'll be x times the 3. And again, that's a plus 9 at the end there. So that's our final factorization. That's about it. Let's see. There was one student showed me this way to remember the difference in the signs here. You start with, use this acronym SOAP. Okay. The S here refers to the sign of this. It's the same as the sign up here. Okay, so same. Okay. This middle one here, this next sign in our answer, is the opposite. Opposite of the sign in our original expression. We can also say it's the opposite of this because this was the same as that one. So this second sign here is the opposite, O for opposite, of the first sign. And this AP it stands for the last sign here, and it says always positive. Always positive. That refers to this last sign right here. AP, always positive. I don't know if that helps you to remember the formulas here, because you do have to remember these trinomial forms here for the factoring of the cubes, sum and difference of cubes. You have to remember these forms. So practice them enough, it won't be a problem. But sometimes students mix up the signs. And this is an acronym that might help you with remembering that. SOAP. Okay, that's it for today.